Hi, I'm making this video using the slide presentation I gave called Flat Earth Reality to a meetup group here locally in New Jersey called Truth Explorers, and I gave that presentation on February the 10th of 2016. My name is Jesse Kozlowski. I'm a surveyor and I specialize in geodetic surveying. I started surveying in 1978, and I became a licensed professional land surveyor in the state of New Jersey in 1990. And throughout my career, I've had the opportunity to work around the world. So the subject of this video is the Flat Earth Conspiracy, as it's known, or it's also known as the Spinning Ball Earth Conspiracy. So you'll hear both of these terms as the people arguing and debating this topic on the internet and really disrespecting one another. The ball earthers and the flat earthers are just at each other's throats over this topic. So you'll hear it both ways. The other thing you'll hear a lot from the flat earth proponent side of the argument is that they are hiding the flat earth from us. They are hiding the flat earth from us. So I chose to make a presentation that focuses on really two general things in this video. One, the conspirators. Who are they? And the second thing is curvature and line of sight. I chose this to really focus on because it's time to get these things straight. There's a lot of confusion being put out there on some of these videos, and you're going to see why during this presentation. The third thing I'll mention on this slide is the audience. Who am I speaking to? I am not debating the flat earth proponents. I'm really going to just be presenting some information in this video that I don't think has been put out there yet in any other video. So right here at the beginning of the presentation, I'm letting you know that if you're someone who's considering these things and you are looking at round earth videos and flat earth videos and watching these two camps battling each other, I'm going to show you something in this video that you have not seen yet. And take it for what it's worth, do your own research, and consider what I'm going to show you in this video. So let's talk about the conspirators. In the videos that you'll watch on the flat earth, they name NASA and the scientists and the historians and the airline industry and the government, and I put these in quotes because they are spoken of as though they are monolithic entities that are all speaking with one voice, all signed on to the idea to hide the flat earth from us. Well, I'm going to add one more to the list that I haven't seen spoken of yet, and that would be the surveyors. Aren't the surveyors part of the conspiracy? Obviously, we're the ones doing all this measuring. Are we signed on to some agreement to hide the fact that the earth is really flat? So here are some pictures of these conspirators. These are surveyors, and you notice right away these are not the surveyors you've seen standing on the side of the road as you drive by. They are not the ones you see on construction sites. Look at what they're doing. Here's a guy climbing up a tower. It's about 100 feet in the air. They get up to the top of the tower, and they're making their measurements to other towers that are 10s, 20s, 30s, 40, 60 miles away in some cases. They have lights on top of the towers because these measurements are made at nighttime so that they can see a great deal further than during the daytime. And the conditions are better for viewing at night. So, and look at the size of the instrument that they're using. This is a gigantic theodolite with a very large circle on it. Gigantic telescope. Here's some more pictures of the same type of surveying being done that I'm going to talk about in this video. And look, they go to the ends of the earth going through enormous effort and hard conditions to do what they did. More on that later as we go through this. If it is a conspiracy, it involves a lot of people. Here's a picture of just one survey department in one city. So it's huge, and there's a lot of people involved. And I'm asking you this: am I one of these people? I'm a surveyor. Am I signed on to the pact to hide the fact that I know the Earth is flat because I've measured it and found it to be so? Well, I'll just answer that for you: no. And I'm here to tell you that the Earth is curved, and I'm going to show you how it is curved. So let's look back. Where did this all start? Where does all this come from? Look at this old picture. Here you find some surveyors way back in the 1600s using a very crude, simple instrument to measure angles, vertical angles to measure the heights, and horizontal angles to measure the location of distant objects, whether they are mountains, church steeples, other prominent land features. Here are some mathematicians doing some type of celestial observations. And what are they doing here? Conspiring to create a fake round Earth globe to represent these on. Yes, right. Okay. So, well, let's go way back. Let's go back to what, 250, 225 BC, thereabouts, where Eratosthenes, calculated the circumference of the Earth, and using shadows from the sun. Oh, I can't talk about that. Sorry, that's off limits. The flat Earth proponents will tell you this individual may not have even existed, this story is concocted, etc., it's not accurate, we can't rely on it. Okay, so I'm not going to start there. However, I will point out that if he didn't exist, but we have a story of how the fictitious character did what he did, we can take the same method that is described in that story and apply it today, measuring the circumference of the Earth today. Look at this video. I encourage you to do it. It's well done. The gentleman physicist asked his subscribers to send in time-elapsed photography, and he got lots and lots of time-elapsed photography all around the world, both in the northern hemisphere and the southern hemisphere. Watch the video. It's very interesting to watch how the shadows move in the northern hemisphere as opposed to the southern hemisphere. I'll leave that for your viewing pleasure. So, continuing on, distrusted, dismissed, rejected. Here's all the things we can't talk about. The space photos. I'm not going to talk about that. I'm not going to talk about the gravity that doesn't exist and the physics and mathematics that are made up by Masonic scientists to hide the flat Earth. Pretty smart fellows, those physicists and mathematicians, to make up round Earth math that kind of looks like it works. But we haven't seen the flat Earth math. I wonder where that is. Astronomy, we can't look at that because there's a big dome up there. Air travel, we can't think about that because the routes are fake and the flight times are fake, even though Max Egan recently posted a video documenting his departure and arrival from Australia to South America on one of these so-called fake routes. GPS, we can't talk about using GPS because it's fake and satellites aren't real, and they are just using cellular towers to triangulate your position. Interesting. History, it's all fake, it's all lies, 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 lies. Well, of course it is, no kidding, but that doesn't make the Earth flat. So, with all of these things scratched off the list, is there anything we can agree on to hold a conversation and discuss this topic? So I'm going to throw this out there. Do we have agreement? Is this a real tool that we can really rely on and trust? A carpenter's level for establishing level surfaces or vertical surfaces? Can we believe that this works? How about a carpenter's square? Can we determine perpendicularness using a Carpenter's square? How about length? Can we rely on units of measure, such as feet and inches, or the metric system, or cubits for that matter, to measure lengths between objects? Is that something we can agree on that is real? Or how about this? A simple instrument like this, just a pendulum with a point on it, that if you hold it and suspend it, in surveyor, we call these plumb bobs in surveying, but we can use this to determine up and down. This points down. Can we agree on that? Or can we agree that if we take a surveyor's instrument, that we can measure the angles between distant objects and find out the angular relationship between those objects? Is this based in reality? Can we accept that when we drive across a bridge, some of these magnificent structures that have been built, that they were built using the tools and methods that I just showed you in the previous slide? These are gigantic structures requiring extreme precision and accuracy to keep these surfaces plumb, to bear these loads. Do we accept that this is real? Okay? How about these buildings? These are some of the tallest buildings in the world. How did they get there? Do we accept, do we trust the methodology to assure that these are truly vertical, to bear the load? How about, do they have square corners or angled corners? And some of these shapes, how do we do that? Can we use the tools I showed you in the previous slide and the ideas behind creating vertical, plumb surfaces and relationships? How do you do that? If we can accept these things as being real, then I'm going to propose that we're going to take a fresh look at this whole Earth curvature thing using some old methods. So I'm proposing a new start using old methods. So yeah, no GPS allowed. Not going to talk about orbiting satellites. So to carry on with this idea and this proposal to using old methods, with starting a fresh look using some old methods, we have to agree on some terminology, some reference surfaces. What is flat? What's horizontal? What is level? What's plumb or vertical? And then the differentiation between curvature and line of sight. You're going to find these terms are constantly being used interchangeably as though they are equivalent in some of the flat Earth videos, and they are not. These are very different things. So keep that in mind as we go forward here. So let's go back to the 1600s, when early triangulation really begins to be used, and used a great deal, and developed using some very basic instrumentation and methodology. Heights of buildings are determined, the locations of distant peaks, mountains, church steeples, so on and so forth are determined using early triangulation. And it's not rocket science. It's just using proportions. That's all. Basic premise here, without any math involved. If you can measure one distance in this shape, you can compute the lengths of all the other sides using the angles and the proportions of that length. That's it. And using this methodology, we've made maps for centuries. So again, measuring these angles, the horizontal angles and the vertical angles, and a base length someplace, you can calculate the positions of everything else in the scene, everything else out, on the landscape. Now, it begins as a local problem, a very practical problem. For instance here, how far is it across the river? Well, they measure this length right here. They measure these angles, and in this case it's a right triangle, and they can easily calculate the length across the river for a very practical reason. Maybe they're going to build a bridge. I don't know. But they want to know what that length is. They can easily do it using trigonometry and triangulation. And when they're done there, maybe they're going to measure the distance from this building to that windmill there, and from that windmill to that mountain, to this church spire. It seems that every town had a church steeple in it, and it can be seen from other towns. And from one church steeple, you could probably see 4 church steeples at all the towns around you. And when you do that, you're suddenly making maps. You're making maps of where your town is related to other towns. You're making maps showing the roads connecting the towns, the rivers flowing between these towns. And as you do this over time, and we're talking decades, possibly centuries of map making, soon you're expanding this across continents. Here's a map showing the trigonometrical survey of India. This is in the 1800s. I don't know if you can see it. I'm going to zoom in to show you it. These are chains of triangles that were literally measured with theodolites. So we're going to zoom in, and here we are at this northern part of the triangulation. Here we can see what are known as arcs of triangulation. And here we can see Mount Everest. And if you can see it, obviously they did not go up there with an instrument, but they did measure lines from these stations here. And in fact, they measured lines to all these prominent mountain peaks in order to calculate their height and their location. Well, over time, through the late 1700s and into 1800s, with all of these measurements being dealt with and computed, gives rise to the body of science called geodesy, which is really focused on the size and shape of the Earth. I'm not going to go into all the details there. It's really an interesting topic. Go ahead and research it. But the main point to make here is that curvature is something that is observed, not manufactured. It is not concocted. Okay. So if we look at this triangle on the right, it is a plane triangle. And everybody knows that the angles of a triangle add up to 180 degrees. Well, as they were measuring these long arcs of triangulation, with distances in the 10s to 20 or 30 miles between points, they began to realize that what was vertical here is not vertical there. In fact, these two are inclined to one another. And when they go ahead and add up the sum of these triangles, it's greater than 180 degrees. And this is where spherical excess was discovered through measurement. And you can read about that. So keep those things in mind. We're going to touch on that some more in a little bit. Right now I want to kind of change directions a little bit and look at some of the flat Earth videos that I've seen on the internet, on YouTube. Here's one that deals with the curvature of mathematics. He does have the formula right. 8 inches times the miles squared. It's approximately correct, but his application is wrong, and I'm going to show you that. Just wrong, okay? Here's one. He's doing some experiments, and he, again, he's one of the ones that does confuse flat with horizontal, and I'm going to show you that. Now this video is a beautiful video to look at. He calls it 33 Proofs that the Earth is not flat. He's using some sarcasm here because he shows some beautiful places in the world, some very tall mountains, gigantic mountains, tall waterfalls, huge valleys, and of course, the fact is that they're very high, and the point is that the Earth is not flat based upon these features. Okay, this video is one that I'll spend a good deal of time on, and that is the Flat Earth Proof number 3, Land Ho. So, okay, let's take a look at some of these. Let's go back to this video, the 33 Proofs. Like I said, he does show some beautiful landscapes, beautiful photography. Take a look at the video. The one thing is that he quotes the elevations and the heights of these land features. And I asked him, where did you get the information? Is this off of Wikipedia or what? What was the source of the information? Where are you coming up with these, great heights? What methods were used? Well, I encouraged him to go look up some of the reports that talk about how that was done. Well, here's one. Here's the, I'll discuss India here. There's the theodolite that they lugged around for years and years, setting that thing up over and over again, measuring all those angles. Here's that map. Here's the northern portion of that map showing this arc of triangulation. All right? And all of these intersection lines measured using that theodolite. And there's Mount Everest, okay, and all these other mountaintops. By people like this, surveyors who have gone out into the wilderness, living, really going through arduous, conditions, circumstances, and, pretty much roughing it out there. And we're supposed to believe that they've conspired to hide the flat Earth. Okay. Here's this other video about the experiments where he's quoting distances. And I'm asking, well, where are you getting this distance of 4.07 miles? 4.07 miles. Where'd you get that? Oh, it looks like Google Earth to me. Disqualified. You don't get to use Google Earth, okay? Because you've already stated that they're lying to us. So that's NOAA. It's the U.S. Navy. It's the National Geospatial Agency. What are you doing using, Google Earth? That's supposed to be entirely fake, right? I bet you can't even measure 50 feet. Okay, the same person makes this type of video, and he says here, not to scale oversimplification. Oh, you think? The way you have this drawn? That's around 3,500 miles. That's what that looks like. 3,500 miles. That is not the distance across Lake Ontario. And therefore, when you make a video and you draw sketches like this, saying that this is over the horizon by 850 feet, you're wrong. You have applied the calculation to the line of sight, and you can't do that. And I'm going to show you why shortly. So, why don't you try drawing to scale? Don't draw like this. All right? So I'm going to show you this video. Did a nice job. Strong evidence of a flat Earth. And he uses a CAD program, computer-aided drafting program, a drawing program on your computer to draw accurately, and he did a great job of it. And yet, through the video, he's talking and trying to get across the idea that you're not supposed to see from here to here. But the fact is, you can see from here to here. So? So? It doesn't make the Earth flat. But guess what? It looks pretty flat, doesn't it? Yeah. Well, I encourage all of these flat Earth types that are making these videos to do the same thing. Get a drawing program and record and draw, and you're going to learn something. You're going to learn something very special. Anyway, I give him a check for a good job, nice job, even though he's really trying to tout the flat Earth. He's not convincing. All right, now to this video here, Flat Earth Proof 3, Land Ho. He even shows a picture of a surveying instrument, and he uses the word level several times, and I will tell you incorrectly. He shows lots of places in the world where you're not supposed to be able to see what you're seeing because, he says, this curvature is hidden. And at 60 miles, this is supposed to be 2,000 feet over the horizon. You're just wrong, dude. You can see the Statue of Liberty from 60 miles, so what? Of course you can. And I promise you, if you go up on top of Mount Everest, you can probably see over 200 miles. So what? Okay? Now, this is where I want to focus a little bit of attention to this whole missing curvature topic. Philadelphia, near and dear to my heart. I live near Philly. That's the skyline of Philadelphia as seen from a place called Apple Pie Hill, which is very close to me here in New Jersey. And in this video, he talks about 335 feet of missing curvature. He also quotes the distance from Apple Pie Hill to Philadelphia. He's off by about 10 miles. I don't know where he got his information. Anyway, I started thinking about Apple Pie Hill. I was on an airplane ride. This was 11, 16, 15, 16th of November. And I was thinking about what he's talking about. And it suddenly dawned on me that he's talking about using the Earth curvature formula, and he's applying it to the line of sight. And he wants us to believe that that's supposed to be over the horizon. Well, he's wrong. That formula is to be applied to the horizontal plane called your local geodetic horizon, which is perpendicular to your standpoint. Likewise, from Philadelphia, and again, I didn't know what building I would see, but I wrote down Liberty One. That's a tall building in Philly. If I was there, my local geodetic horizon would slice out, and I could compute the curvature drop here, not from the line of sight. No, you got that wrong. So I'm going to show this to you. Here's a picture that you could get in any surveying textbook. And you can see here there's a line of sight and there's a horizontal line. They're not the same thing. Not at all. Level surface, I'm going to leave that out of this discussion for right now, but we could touch on that as well. The point that I want to make here is that the curvature calculation is computed from the horizontal, not the line of sight. So all you guys making those videos, go back, take a look again, redo your videos, and you're going to make a different video. I promise you. You're going to reach a whole different conclusion. Okay. So I went up to Apple Pie Hill, and I made some measurements. There's a fire lookout tower on the top of Apple Pie Hill. And there's my instrument sitting up there. Here's a shot of it sitting on top of the platform that is 46 feet above the ground. And here it is. This is a wild hairbrug. It's an old-fashioned theodolite. There are no electronics in it. It's a 1 arc-second, very precise instrument. And I'm going to play a little video for you to see what it was like up there. My iPhone is not capturing Philly, the skyline, but it's right there. Philly's right about there. There's me being cold. There's my wind gauge.
That's my wind gauge.
Yeah.
It got calm all of a sudden. Time to take a reading.
All right. Gives you a sense of what it's like on the top of the fire tower at Apple Pie Hill. Okay, for completeness sake, I'm including my field notes. I measured zenith angles to the tallest structure I could see. I did 4 sets. That's my average zenith angle to the top of the tallest structure. I also made a note over here, which I will zoom in on for you to see. This was the 20th of November. That's the tallest visible structure. At the time, I did not know what building that was. I made my zenith angle measurements to the top. Here's the interesting thing that was well worth the trip to go up there. I set my telescope at 90 degrees. That is, I created my local geodetic horizon, and I created a line of sight through the local geodetic horizon, slicing through the building. All right? So understand that. This is the local geodetic horizon at Apple Pie Hill, slicing through that skyscraper. And I made this note. It appears to be about a quarter from the top, a quarter of the way down, just roughly estimating that. So here I grabbed this picture off of, just using Google, of shots of the Philly skyline. This is the Comcast tower, and that's what the building looked like. This is where my telescope crosshair sliced through the building. That is the horizontal from Apple Pie Hill. It is from this reference that you can calculate the drop of the curvature. Just think about that. Earlier in the month, on November the 9th, I decided to do a little experiment to measure curvature from, on one line at either end of the line. I chose 1 mile. I could have chosen 1,000 feet. I didn't use 1,000 feet because the question would be, well, how did you measure your 1,000 feet? How do you know it's 1,000 feet? Well, in this case, I used a state highway, a north-south running highway, and I used the milepost at 27 and the milepost at 28. So I'm going to believe that's a mile. That's it. I didn't measure it. Now, if the Earth is flat, the sum of the angles would be 180 degrees. So here I am at milepost 27. I put a nail in the pavement here. That's my T2 1 arc second theodolite. Here I am at milepost 28, doing the same thing. Made zenith angle measurements from both ends of the line. Here are my record, my field notes. I did 6 repetitions at this station, and I did 6 repetitions at that station. You can look at that stuff on your own. I'm going to just get right to the conclusion of that. What you find out is that these terminal ends of the line, the sense of vertical at each end, these are not parallel. How much are they not parallel? By 1 minute and 11 seconds. Okay? Now the math, if you do the math in a mile, it's supposed to be about 52 seconds, but that's a rough approximation. You really need to take into consideration what latitude you're measuring from. Why? Because the Earth is not a perfect sphere. It is an ellipsoid. And so these things change depending upon where you are on the Earth. Roughly, though, for our conversation, it's approximately 1 arc minute per mile. So let's think about that. If we repeat those measurements for many miles, what do we get? So I measured between milepost 27 and 28, and I got 1 arc minute there. Now, if I were to go set up on milepost 29 and measure back to 28, 28 to 29, etc., measure both ends of the line from 29 to 30, 30 back to 29, and continuing up the road, 31 to 30, 30 to 31, and last here. So I'd have 1, 2, 3, 4, 5 sets of zenith angles each mile. How do these measurements of 1 arc minute per mile fit a flat Earth model? Someone tell me, please. I don't know. How does that work? Whereas these measurements of 1 arc minute per mile fit the ellipsoidal Earth model very, very well. Okay? So someone may say, well, okay, did you repeat those measurements? No. I already spent a day doing this right here. So you go do it. Somebody else go do it. I've already done it. And guess what? It has already been done. And has been done all over the Earth. Here's a triangulation diagram. Here's Apple Pie Hill. Here's all the measurements made from Apple Pie Hill. And as you can see, each one of these triangulation stations also measures all these triangles. So what I'm telling you is, these are very long lines. They're not 1 mile, they're very long. And if you get the field notes, which are available to you, you can write and get the actual observations made, you will find out that these angles, these vertical angles, reveal Earth curvature along this direction, and along this direction, and in this direction. Yeah, it does. And in fact, we have hundreds and thousands of miles of these types of measurements all across the country. You can't really see it, but these little colors are arcs of triangulation across the United States. And we have not only the United States, but all of North America and Alaska. And they measured across Siberia there. And we have South America. And look at Europe. It's pretty well measured. It's so measured it's black there. Look at all this triangulation coming across here. Look at the triangulation going across to Greenland and across and over into Europe. So it's been done all around the world for hundreds of years. And all these measurements add up to the experiment I was indicating to you, going on for 1 mile after 1 mile after 1 mile up a state highway. Do we know that the Earth is curved? Yeah, we do. And in fact, it's not a secret. You can read about this in all these books that are available for download as free PDFs. Just search these titles on Google, and you can download these PDFs of these very old books on geodesy, on surveying and geodesy. Here is the figure of the Earth, an introduction to geodesy, 1881. The figure of the Earth in isostasy from measurements in the United States. And I love this one. A history of the determination of the figure of the Earth from arc measurements, 1906. So I ask you, where is the Flat Earth Math book? Is there a secret book of Flat Earth Math hidden away someplace? Does anyone have a copy of it? And that these are all fake books of mathematics showing that the Earth is round? Is that are we supposed to believe that? Come on. Oh, here it is. Oh, no, wait. It's flattening the Earth. It's not flat Earth. Flattening the Earth. What's that mean? Well, that means here we have 2,000 years of map projections. Yes, what do map projections do? Well, they flatten the Earth. John P. Snyder wrote this book. He's a very smart guy. Wrote this book. He also wrote this book, A Working Manual of Map Projections. Maps are 2D projections of a curved surface. And in this book, you can read all about these shapes, the cylindrical projections, the conical projections, and azimuthal projections, and there's many others. So I'm telling you, we've gone from paper maps to phone apps. If you pull out your smartphone and you want to get from one place to another, you know, a globe does not pop up out of your phone, but you will see a display of a map that is based on one of these projections, and that's how it works. Okay? We used to pull maps out of our glove box and unfold them. So we don't do that anymore, right? So here's a cylindrical projection. Here's the idea. You have the globe. You project the land features onto the cylinder, and then you cut that cylinder and roll it out, and you have a map, flat piece of paper. Of course, doing that, you're going to get distortion in places like this. Here we can take the conical type of a projection. You put the cone onto the Earth, project the land features onto that surface, cut it, roll it out, you've got a map. There's all kinds of map projections. Here's one that looks to be like you take scissors and you cut the globe apart to try to retain the shape and continuity of all these land features. And that's how that one works. But you can do it mathematically. Well, here's a map projection. I won't even call this a map projection, but this picture has been getting a lot of play in the Flat Earth videos, and they're trying to tell us that this is how the Earth really looks. Okay, and they're actually saying that the United Nations has adopted this as their map, as their flag, because, quote, they're laughing at us. They're putting this right in our face, and they're laughing at us that the Earth is flat. So really, seriously, you really believe that's Australia? You believe that's what Australia looks like? You're actually looking at a globe. If you take a globe and look straight down on it, this is the type of view you'll have. And that's what that is. Now, I got interested in where did this whole idea of the UN laughing at us, with their flag, where did that come from? What projection is used on that flag? Well, you can get this fact sheet right here, and it says here they chose the polar azimuthally equidistant projection to make that map. Hey, I'm no fan of the UN, okay, but I am going to tell you that I also found this on the UN website. Well, this too. And this one right here. That's what Australia looks like. So take your pick. There are a lot of different map projections that you can use for different purposes to minimize distortion where you want to retain the best shape. And I like the one in the middle there. It was just Valentine's Day here. That's the Valentine, the Valentine projection. So here's the flat Earth reality, folks. The Earth really looks flat to us. It sure does. But we really can measure the curvature, and we really have measured the curvature. And we don't have to go into outer space to do it. We've done it for hundreds of years. And we really do know the real size and shape of the Earth. So I'm going to show you this to offer you the perspective. For all you people who keep talking about no matter how high you go, the horizon comes up to your eye, and you go up so high and you can't see the curvature. Well, let's go the other way. Let's go small. Here's a soccer ball. Now this we can see. I can see that that ball is round. And if this was you standing on that soccer ball, you would be microscopic. And the distance to the horizon would be nearly microscopic. But I can tell you, it's so short that it might as well be flat. So what I'm saying to you, for you that keep saying that no matter how high you go, the horizon reaches your eye, take this soccer ball and smash it up against your eyeball and tell me if you can see that it's curved or flat. That's all you're talking. That's what you're really saying in the opposite direction, really. So here's the reality. The Earth is an ellipsoid of revolution. Here's the dimensions of it, and we know that to be true. And here are some final thoughts as I try to wrap this up. Go ahead and research the history of geodesy. It's probably a topic you've never heard of. And there are hundreds of years of measurements. You can read about expeditions that took years and years and years to perform. In fact, read about the one in the 1740s when they couldn't decide if the Earth was oblate or oblate. And they sent an expedition to Lapland to measure an arc of triangulation in that latitude, and they sent an expedition to Peru to measure an arc of triangulation at that latitude. And they wanted to find out which one was longer, to once and for all settle the true shape of the Earth. They knew it was round, they just didn't know exactly which way it was round. So, took a long time to do. I'm sure that some people suffered greatly on these long expeditions. I'm going to suggest to you that you start making measurements, make less videos, make some measurements, and then make some videos about those measurements. By the way, if you can't make the measurements, go find someone who can. Get some help from somebody who knows how to make some measurements. Then make a video. I think you're going to make a different video than you've been making. I'm going to emphasize to you to stop parroting and stop being a repeater and, letting others think for you. Don't do it. Experiments. If you're going to do these experiments that you're making all these videos about, be sure to define the horizontal reference, because when you do that, you will then stop confusing curvature formula being applied to the line of sight as opposed to your horizontal reference at your location where you are looking out at that remote object. Time and effort. I liked what Max Egan said recently in a couple of his videos where he's actually taken up this topic to basically tell people do something else that makes a real difference. Stop arguing and hating each other, and it's just ridiculous the way people are going after each other, whether you're on the ball Earth side or the flat Earth side. Knock it off. All right, this thing has become a huge distraction. The only reason I would take the time to make the video I have is because I think in this video I've offered something that you have not considered, and if you do, it's going to open, it's going to open your eyes, and if you look at it, maybe some light bulbs will turn on for you, and you're going to see this a lot differently. Some of you who are making these flat Earth videos might choose to start making other videos once you realize that this curvature formula has been applied backwards. Okay, and so that's it. The other thing I'll say is go outside. Get away from your computer screens. Go out, look up, look around, pay attention, look at the sun, the moon, the stars, go sleep outside, spend some time out there. Yeah, do that. Not even touched on. GPS. Yeah, I left that off. GNSS. Bet a lot of you don't even know what that is. Astronomy. VLBI. LIGO. Antarctica. Sea levels. Oh, yeah. Different sea levels. Yeah. Space geodesy. Very interesting topic. By the way, all of this is open source, public information involving many, many thousands of people all around the world. Have fun, people. Peace.